Hi, my name is Christian Scheffer. I'm from the University of Münster from Germany, and I will talk about a hardness proof saying that scheduling 3 trains is NP-complete. So in general, we consider different railway stations that are connected by railway tracks, and now we would like to move a train from one station to the other station. And now we model these tracks by curves lying in the plane, and the trains to be moved are modeled by subcurves of these embedded curves. And now we have to move the subcurve from the one side or from the start position to its target position. Now furthermore, we could also have different tracks and different trains lying on these tracks, and now we want to move simultaneously the trains from their start positions to the target positions, at which we would like to avoid collisions, as illustrated here. Now furthermore, of course, we do not only have curves that are straight lines, but also curves that have sharp curves, as illustrated here. Now, in order to simplify the following illustrations, we illustrate the train to be moved along the tracks, not as sub-segments, but as points moving along the curves, as illustrated here from start position to its target position. So now the general problem setting is described as follows. We have a set of curves modeling the tracks, and furthermore we have trains to be moved along their specific tracks from their start positions to the target positions. And now we would like to move all the trains simultaneously along the tracks, such that the time needed until all trains achieve their target position is minimized. So here in this example, the train that has the largest traveling time is the blue train, and so the time which is needed by this blue train is now defined, or is called, the make span of the corresponding schedule. And now it's our goal to compute schedules moving all the trains along the tracks with a minimal make span. So in a previous paper we showed that the general problem setting for arbitrary many trains is hard, which in particular we showed that there is no f-pitas unless p equals np. Now the main idea of the proof is the following. It is a reduction from the 3-set problem as follows. We consider an arbitrary 3-set formula and construct a corresponding set of tracks for which we have to compute a corresponding schedule, fulfilling a specific or carefully defined required make span. Now the construction is as follows. For each variable we have 2 tracks. The first one corresponds to the variable and the second one corresponds to its negation. So here in this example we have 4 variables, which means that we have 8 tracks, which we also call variable tracks or literal tracks. And furthermore, and these literal tracks go from left to right. Furthermore, we have for each clause a corresponding track. So this is a clause C1, and here's a corresponding vertical clause track. And now we, based on a variable assignment, for example, v1 is assigned to false, v2 is assigned to true, and so on. For such a specific assignment, we construct a corresponding schedule as follows. Each literal track that is not fulfilled by this assignment has to wait for 1 time unit, and the other corresponding literal does not have to wait. And now the entire construction fulfills or guarantees that a train traveling along a literal track collides with a clause train if the corresponding literal is not fulfilled in the corresponding clause. So here in this case, the assignment says that the negation of v4 is fulfilled, implying that the variable or the literal v4 is not fulfilled, which implies that we have a collision between the literal track corresponding to the negation of v4 and the track or the train corresponding to the clause C2, which implies that the train on clause C2 has to wait for one time unit. And this in turn implies that each clause is fulfilled if and only if the corresponding train on this on the corresponding track has to wait for at most 2 time units. So here in this example, also the train corresponding to C1 has to wait for 1 time unit, and the train corresponding to C2 has to wait for 2 time units, and that's it. So this is the overall idea of the reduction. So now in the current paper we consider the situation that we have only 3 trains to be moved along their corresponding tracks, which means from continuously from their start positions to their target positions. And as illustrated here. And here we showed that even the problem of scheduling only 3 trains is NP-complete. So the main idea of the proof is we consider the 3-dimensional parameter space of the 3 input tracks, which means each point in the parameter space corresponds to a configuration of the tracks of the trains lying on the specific tracks. So for example, the point bottom left corresponds to the configuration that each train lies on its start position, and the position top right corresponds to the configuration that each train lies on the end on its target position. So this also means that we have some parameter points that are not allowed, and these are exactly these points that correspond to configurations in which at least 2 trains collide. So this in turn means that computing a schedule moving the trains along the tracks from start positions to target position corresponds to computing a path connecting, or a curve connecting the bottom left corner with the top right corner inside the parameter space, at which the not allowed parameter points have to be avoided. And furthermore, as we want to compute a schedule moving as fast as possible all trains from their start positions to their target positions, which means a schedule with a minimal make span, we want to compute a shortest 3D path from the bottom left corner to the top right corner. So the general idea of the proof of theorem 1 is the reduction from a 3D shortest path problem, which is NP-complete, to our scheduling problem. Now in particular we need a specific 3D shortest path problem such that, or which is realizable by our reconfiguration problem, which means by the by tracks of an instance of our reconfiguration problem. In particular, these specific type of 3D shortest path problems, or their constructions or instances, are made of planks as illustrated here, and all these planks lie above each other. So for example, consider 2 tracks, capital X and capital H, intersecting in this point here. So this intersection produces a plank as illustrated here in gray, at which its extension regarding the x-coordinate corresponds to the length of the train on curve capital X, and the extension of the plank along the h-coordinate corresponds to the length of the train on track capital H. Furthermore, the extension of this plank regarding or along the y-coordinate is infinity, because for the collision of the two trains on the tracks capital X and capital H, it doesn't matter at where the train on track capital Y, which is not illustrated here, is located. So its position is irrelevant for a collision of the two tracks on capital X and capital H. Now, the general key components of this specific 3D shortest path problem are the following. First of all, we have some path splitter gadgets which double the number of the shortest path for this specific instance passing through this path splitter gadget. Furthermore, we have three-way path splitter gadgets which triple the number of the shortest path passing through this gadget. Then we have some path shuffle gadgets which shuffle the geometric shortest path. So here 1, 2, 3, 4 into the order of 1, 3, 2, 4. And finally we have some path blocker gadgets that block some geometric shortest path passing through this gadget. So now for our specific type of these 3D shortest path problems, we can show that it is complete to compute corresponding shortest path. And finally, by applying our technique for constructing planks as intersections of two corresponding tracks, we can construct curves realizing whose parameter space corresponds to the corresponding gadgets. So this is a triple of curves constructing the splitter gadget. This is a triple of curves constructing as a parameter space the three-way path splitter gadget. This is a shuffle gadget, and this is the blocker gadget. And by combining all these subcurves in the corresponding order of the 3D shortest path problem, we obtain a complete construction of three curves which corresponds to the original 3D shortest path problem. So that's all I wanted to say, and yeah, thank you for your attention.